in the previous video clip, we looked at what was not suspect. Previously, we'd seen time was suspect, length was suspect with time dilation and length contraction. But last time we saw that the transverse dimensions, when you're moving along in a certain direction, that the transverse or perpendicular dimensions, width and height, are not affected by that motion. We get the same results for any observer looking at that, observing that. And as I also mentioned, that another name which really never caught on for the theory of relativity was the theory of invariance. And so what we want to consider here, it is important that you have these invariant quantities, and we want to look at a quantity called the invariant interval, because it's going to be useful for us later on when we look at the so-called Lorentz transformation, which is the relativistic version of the Galilean transformation we considered earlier. So let's set up this situation here. We've got Chris and Bob and Alice, and we're not using C for Chris but K because we don't want to get it mixed up with C for the speed of light. That's the only reason there. So we're going to consider the time and distance between two events as observed in different frames of reference. So here's the situation. Alice this time will be the stationary observer, at least from her perspective, of course. And Bob is in a spaceship traveling with velocity v, and Chris is in a spaceship traveling with velocity 3v, or just doesn't really matter what that is, just pick 3. It's a velocity that is faster than Bob is traveling. Okay, so that's the setup here. On Bob's ship, we're going to look at a light clock that he has, and from his perspective, of course, he's just stationary. He sees the light clock bouncing up and down. And the two events we're going to consider are when that light pulse starts going up, so maybe a little flash of light or something will indicate, hey, the light pulse is going up, hits the top mirror, and then comes back down again and hits the bottom mirror, and that will be event 2. So event 1 is the light pulse going upwards on Bob's clock. There's event 1. Event 2 is the light pulse coming back down, maybe just a little flash of light or something to indicate at that point in space and time, according to Bob, those were the two events. Now let's consider what Alice would observe looking at those two events on Bob's clock. Let's assume the first event here, that upward flash, or the flash as the light pulse went up, occurs right here. They're all together. And then, of course, in the instance after that, Bob is moving that way. Chris is moving even faster that way. So Alice is now looking at the light clock on Bob's ship. What does she observe? Well, she observes our classic triangular diagram we've seen before. She's going to see Bob's light clock moving that direction. So here's snapshot 1 she could take when the light clock the light pulse just takes off. So there's event 1. She'll see the light pulse moving at velocity c here. Let's put that in, of course, just to remind ourselves. It's velocity c there. Same thing here. C. We'll get to Chris in a minute. So she sees the light pulse going up, hitting the upper mirror. It takes another snapshot there. Again, then the light clock is here, and then the third snapshot, when it comes back, the light pulse comes back down again, and that would be event 2. So she sees, according to her frame of reference, her lattice of clocks and measuring system, she sees, of course, event 1 and event 2 at different places. Bob sees event 1 and event 2 occurring at the exact same place, right, at point 0 on his clock, his measuring system from his frame of reference. And then what does Chris see? Well, remember, Chris is going, say, 3 times as fast as Bob. So the first event occurs here, and she makes note of that. Then, however, of course, when the second event occurs, so Bob goes along here, maybe the second event occurs when he's right here, right? The light pulse goes up, comes back down again right here. Whereas Chris at that point, she's actually, about 3 times farther down the road there. And therefore, she will see event, in her frame of reference, she will see event 1 here, right? There's event 1. But event 2 will occur behind event 1. Because imagine, she's gone farther. She's looking back there to Bob and sees event 2, the light pulse come back down again. So her diagram, again, it's a triangle, but she will observe the light going in a different direction than Alice will. So again, this is C here, speed of light. And so she sees event 1 occur here. Watching Bob's light pulse, looking behind her, she'll see it go up, hit the top mirror, come back down again, and then again she's way down here now looking back at where event 2 occurs behind her. So that's what she will see. Let's put a couple other things in here because we want to do a little analysis of what's going on. I put the height of the light clock, we'll call it h this time. As we talked about in the last video, and I just mentioned a minute ago, those transverse or perpendicular dimensions are not affected by motion in this direction. So h here, the height of the light clock, will be the same for Alice and will also be the same for Chris. They will all see the height of Bob's light clock as h. That will not change, and that is a key point here in what we're going to derive in a minute. But we needed to find another quantity, and that is we wanted to find the distance between the two events. Clearly for Bob, the distance between the events is essentially 0. We'll assume they're, we drew them a little bit apart there, but we'll assume they're exactly, light pulse goes up, comes back down, hits the same spot there. For Alice, however, we'll say this distance here between the two events in Alice's frame of reference, we'll call that x sub a. Okay, obviously a for Alice there. And similarly for Chris, distance between the two events in Chris's frame of reference. We'll say it's like this, x sub k. And that's why we want Chris with a k, not a c, because it might get confusing with the speed of light there. So x sub k, x sub a. We could also define x sub b, which would be 0. Distance between the events, as far as Bob is concerned, is 0. So that's the setup. We can clearly see they have different perspectives on those things. What we want to do now is use a little bit of the Pythagorean theorem, right? So we'll remind ourselves of that and see where that leads us here. So I'm going to erase this. We have that now. So let's consider Alice's case here first. Okay? We've done similar analysis when we did the light clock, first light clock analysis. Let's sort of redraw the triangle here for Alice, roughly. Something like this, more or less, right? And we said this distance here is x sub a. So I'll put it in here, x sub a. And we said that speed of light is c, okay? And we will assume that one tick of the clock is a round trip, up and back again. Okay, so we didn't put that in there, but we'll say t sub a, we'll just define it here, t sub a equals one tick of the clock from Alice's perspective. Well, what is that one tick? It's up here and then back down again. What is this distance? It's the speed of light times half a tick, right? Because this is half a tick here, this is a full tick, and so we can say speed of light, velocity, times time is distance. So this distance here is c ta divided by 2, that leg of our triangle. And by symmetry, this other leg is the same thing. That's c ta over 2. And then this here is xa. Okay, so now we've defined the three legs of this triangle. So this is the triangle we're looking at right here. I've just redrawn it up here. This is the distance xa. Just by definition, we say the distance between the two events, that's xa. The time of travel for the light pulse, up and back down again. Not the time, well, the time of travel is ta, up and down. So ta over 2 is up and ta over 2 is down. And the distance is the speed of light times that time of travel. So c ta over 2 is the distance of that part of the leg. xa is the distance here. Ct over 2 is the distance of that part of the leg. Now you may remember, of course, that the Pythagorean theorem applies to right triangles. And we don't have a right triangle here, but we can draw, cut it in two here, and that's a nice right angle there for us. That's again xa there. So now we have another triangle we can actually work with here. So this is the triangle we're going to apply the Pythagorean theorem to. It's essentially half of that triangle. So this distance here is half of the whole distance by symmetry. We've cut it down the middle here. So this is xa over 2. So this is xa over 2. This leg here is c ta over 2, speed of light, times half a tick by definition. And what about this part here? Well, remember, that's just the height. That is the height of our light clock, Bob's light clock. And so this is h. And this is the right angle. So now we can apply the Pythagorean theorem. So let's do that. I don't think we need Bob and Chris's picture anymore here. We can sort of remember what's happening with that. And Alice. Okay, so Pythagorean theorem applied to this triangle. So we'll bring it over here. And we say, okay, this side squared plus that side squared equals that side squared. So what do we get? We get h squared equals xa over 2 squared plus, oops, sorry, that's not what I want. Hypotenuse, of course. Hope you caught that. Try this again here. So get rid of the equal sign. Let's do this. H squared plus xa over 2 squared. H squared plus xa over 2 squared equals the hypotenuse squared. Just got ahead of myself there. So equals hypotenuse c ta over 2 squared. Okay. Let's just multiply that out a little bit. You know, we've got, so we'll do every step here. H squared plus xa squared over 4 equals c squared ta squared over 4. Just squaring each of those terms. And then let's just multiply through by 4. I'd like to get rid of these 4s in the denominator, just clean it up a little bit. So multiply everything by 4. So I get 4, you know, if I do it on both sides, of course, it's legitimate. 4h squared, and then plus 4 times that just gives me the xa squared, and I get rid of that one as well. In other words, I can have this. I got 4h squared plus xa squared equals c squared ta squared. Okay? And I'm going to do one more thing here. I want to get the xa and the ta on one side. So we're going to write this as 4h squared equals c squared ta squared minus xa squared. Okay? So that's my analysis. Just we started with Alice here. We just said, okay, we'll define the distance to two events as xa. We know the speed of light is c, so we know this distance it covers. If we define one clock tick, ta, the time from here to here, this is cta over 2, half of the time. And then when we do the triangle and split it in two, we get xa over 2 here. And then we just apply the Pythagorean theorem, realizing that we've defined the height to be h. Do a little manipulation there, and we get this. And you might be saying, well, big deal. What's the deal here? So that's for Alice. Note that we could do the exact same analysis for Chris here. Now, hers is going backwards, but we have a triangle for her. We'll just do it on the triangle here. We will assume that T sub k, here T sub a was 1 tick for Alice, so here for T sub k equals 1 tick for Chris. Okay, this was for Alice. Again, they're all observing Bob's clock. So this is 1 tick on Bob's clock from Alice's perspective, her frame of reference. 1 T sub k, 1 tick on Bob's clock from Chris's perspective. Of course, 1 tick, again, is all the way up there, all the way down there. So she will see slower ticks than Alice will, and Alice sees, they both see slower ticks than Bob does, the time dilation effect there. But we have the exact same triangle. Again, we can split this in two. This whole thing was xk. So the triangle we're going to be looking at here is, we'll do it in green just to show it there. Roughly that triangle. This, here's the height. That's the same. This becomes xk over 2. It's a k there. And this distance here is the speed of light times half a tick. Because, you know, half a tick up, half a tick down. So this becomes c tk over 2. Exact same little triangle as with Alice, just different values here. Okay, we have h is the same. That's going to be important here in a minute. But we have ctk over 2 versus cta over 2, and xk over 2 versus xa over 2 here. we could do the exact same analysis, draw the little triangle, do the Pythagorean theorem. We get the exact same result, except instead of TA and XA, we'd have TK, T sub K, and X sub K. And so, let's see, where are we going to put this? Okay, so here, I think we can get rid of this now. You know what we were just doing there. Okay, we'll leave Alice's triangle up for a minute. There's Chris's triangle. So Chris's result would also be 4h squared. H is the same in every case here. 4h squared equals c tk squared minus xk squared. Okay? And what about Bob? Let's consider Bob here. I guess we'll get rid of Alice's triangle here. So again, so Alice's triangle would be that. That's what we analyzed there. Well, Bob doesn't have a triangle, right? He has, his distance x here is 0. But note for him, oops, I forgot. Got to get a c squared there. Hope you notice that. Easy to lose these things as you're doing these things. Always good to go back and double check, make sure you haven't missed anything or dropped anything like that. So both of them, 4h squared, c squared, tk squared minus xk squared, c squared, ta squared minus xa squared. For Bob, what would he have here? Well, he has the up trip and down trip. Okay, so it's h up and h down, right? So that's 2h. So we know that light travels, for him we'll say T sub b equals 1 tick on his clock according to him, according to Bob. The time to go up is therefore c times times half of T sub b, right? And c times T sub b times half of that. So the total distance here for Bob is 2h, okay, h up and h down, or we could also say it is c times tb over 2, half a tick, plus another c times tb, c times tb over 2. You see that? So h up and h down, so 2h total for the distance. And then thinking about the speed of light, it's going velocity c up, velocity c down, and half a tick is tb over 2, because 1 full tick is tb. So c tb over 2 plus c tb over 2, that just equals c tb. So we've got 2h equals c tb, and we'll squeeze this in here. If we square each side, which we can do, everything is positive here, we get 4h squared equals c squared tb squared for Bob. So let's highlight these. So for this is Bob's here. This is Chris's result. And this is Alice's result. And know how I've written them. You may have hopefully caught on by now what's going on here. Or have an idea. 4h squared, 4h squared, 4h squared. H is the same for all of them. Therefore, this equals that equals that. And qualitatively, you can just see that. We've got two events here, event 1 and event 2. H is the same in all cases. H is an invariant quantity. Fancier way to say that. It does not change in all these frames of reference. All of them see H as the same thing. And therefore, 4h squared is clearly the same for all of them. And so what does that mean? It means c squared t sub k squared minus xk squared is the same as c squared ta squared minus xa squared, even though xa clearly is very different from xk, and t sub k is very different from t sub a, because t sub k is 1 tick for Chris. Clearly it's longer than Alice's tick, ta being 1 tick for Alice, which is clearly longer than 1 tick for Bob here, tb there. Yet this quantity, and it's known as the invariant interval. Okay? This quantity is invariant from one frame of reference to another frame of reference. So again, we have two events at different space and time locations depending on the frame of reference. But if you take the location of the event and the time between the events. Okay, so here's what's important here. We've taken the distance between the events, okay, in each of the frames. We've taken the time between the events in each of the frames. So for Chris, she measures the distance between those two flashes, and she measures time on it according to her perspective here, looking at Bob's clock. Alice does the same, and we'll get to Bob in a minute. He's slightly a special case here. But if they actually take their measurements, t sub k and x sub k, and t sub a and x sub a, even though they're different values, and you do this little operation, c squared t squared minus x squared, you get the same value every time. It is an invariant quantity. It's called the invariant interval. And as I mentioned previously, it will be a very useful quantity when we look at the Lorentz transformation, or when we want to actually derive the so-called Lorentz transformation. What about Bob, though, here? Let's just say a word about Bob, because you might say, well, his doesn't look like Alice and Chris. His is different. It doesn't have that second term there. But note that for Bob, the distance between the two events is 0. So really, he has a minus xb squared here. His general form, you could say, is minus xb squared, just like we have a minus xk squared and a minus xa squared there. But for him, xb is 0. The distance between the two events is 0, so that's why it's not appearing in this example, because it's 0. So in general, what we have here is measure the distance between two events and the time between two events in any given frame of reference. Okay, so this is Chris's frame of reference. She is measuring the tick of Bob's clock based on her own light clock she could have with her. Alice is doing the same thing based on her light clock, and they're getting different values for the t and x. Okay, clearly we can see x is different here, xa versus xk, and we can also see tk is going to be different as well versus ta, because, again, different times for the ticks here. And then you've got Bob, of course, being his tb, the shortest of all, and x is 0. In his case, xb equals 0. Even though the time and distances between the two events are different for each of the frames of reference, this quantity, when you do that operation, will always give you the same answer. And it's really based on the fact that h is invariant. The height, the transverse dimension here, will not be affected by motion in, say, the x direction as we've drawn it here. Okay, so that's the invariant interval, and as I've said several times now, we'll see it again when we consider the Lorentz transformation, which is coming up next week, I believe. Okay, let's talk about a real-life example of the special theory of relativity. In fact, a classic example showing that it actually works in real life. It's of a particle called a muon. And it is muons are sort of like electrons, but they're much heavier, about 200 times the mass of an electron. They're also short-lived particles. They decay into other things. And so the average muon lifetime is about 2.2 microseconds, 2.2 millionths of a second. When they get created, they can be created in particle accelerators, but they're created naturally when cosmic rays coming in from outer space hit various atomic nuclei, atoms in the atmosphere, and the resulting sort of spray of particles that comes out of it. Some of those particles are muons. And the height at which they are typically created in the atmosphere is about 10 kilometers. So here's our rough diagram here. Cosmic rays coming in. Some of those cosmic rays get all the way down to the surface of the Earth, but some of them will hit atoms in the atmosphere, and out of those collisions, muons will be generated at about a height of 10 kilometers. We know that if the muon is just sitting there at rest, its proper lifetime, note we put proper in here. Remember we're talking about proper time. In other words, its time at rest. It has a little internal clock, you can imagine, not literally, but internal clock, such that it will live for 2.2 microseconds, just sitting there. So that's its proper lifetime. Its lifetime measured in its rest frame, as it were, its frame of reference when it is at rest. Also, average velocity of these muons created is very, very high, 0.998 times the speed of light. Okay, so not quite the speed of light, but very, very close to it. And so given the fact that we know its lifetime, how long it's going to exist before it decays into other particles, just spontaneously in average, and then also its velocity, 0.998 c. You do a little calculation there. It's traveling very fast, but it's not living very long, not existing very long. And so the distance traveled, about 660 meters is what it comes out to be, the speed of light. This essentially being pretty close to the speed of light, 3 times 10 to the 8th meters per second. But 2.2 microseconds is 2.2 times 10 to the minus 6 for those of you who do those sorts of calculations. And so you get on the order of several hundred meters in terms of the distance traveled by an average muon, supposedly, well, not supposedly, but generated by these cosmic rays, supposedly will travel 660 meters. There's a problem here, however, because at the surface of the Earth, 10 kilometers below where these muons are being generated, we see a lot of these muons. So what's going on? Because according to the calculation here, they can only travel on average 600 or so meters, 600, 700, something like that, and yet they have to go 10,000 meters to get down to the surface of the Earth where we observe them. And we know they are created at about a height of 10 kilometers. So what's going on with that? Well, the explanation comes through the special theory of relativity. So let's imagine, first of all, we're outside now, we're observing these muons. We know their proper lifetime is 2.2 microseconds. Okay? But remember, moving clocks run slow. So as I say, I'm observing the muon's lifetime, it's in the sense it's internal clock ticking away in there, I will see it live longer. Okay, and if you figure out what 0.998 c is in terms of gamma, our gamma factor, gamma being 1 over square root 1 minus v squared over c squared, with this velocity, you'll get, it's about 15, I think, something like that, in that vicinity. So in other words, from our perspective, we will observe the muon's average lifetime increase because its clock will tick more slowly from our perspective as we observe it. In fact, it will tick 15 times more slowly. And therefore, from our perspective, it will be able to travel 15 times longer than this calculation we showed right here. And clearly, 15 times 600 meters is going to give me plenty of distance, plenty of distance for the muon to get down to, well, it'll be fairly close, but 15 times 660 gets you right around to 10,000 meters or so, and so we will see the muons at the surface of the Earth. So it makes sense then. Now you might also ask, though, well, what about from the muon's perspective? Because the muon's perspective, its clock is ticking at 2.2 microseconds in terms of its lifetime. At that point, it goes out of existence. So how do you explain it from that perspective? Well, here's where the other aspect of the special theory of relativity comes in that we've been working on this week, and that is length contraction. So the muon sees its clock just ticking away normally, right? It doesn't know, of course, but we'll say it knows that 2.2 microseconds, okay, lifetime is up, time to decay into something else, give up the ghost, as it were. But how does it then get down to the surface of the Earth? Well, as it's coming down through the atmosphere, it's seeing the surface of the Earth rush up towards it at a speed of 0.998 c. Because remember, as far as this is concerned, it's just sitting there. If you could imagine yourself as an observer, as a writer along with a muon, you'd just be sitting there looking at your little clock, as it were, ticking away up to 2.2 microseconds. You're at rest, but you're seeing the surface of the Earth. In your frame of reference, you're at rest, but you're seeing the surface of the Earth rush up toward you at 0.998 c. And if something is moving toward you at that speed, you have a length contraction effect. And so that contracts the length from 10 kilometers to about 1/15 of that. Actually, sort of around about 600, 600, 650, something like that. And so for the muon sees a length contraction effect that enables it to live only 2.2 microseconds but still get down the surface of the Earth. From the outside observer's perspective, as we're observing the muons, it's traveling the full 10 kilometers, because that's in our frame of reference, but we see it live for a lot longer because of the time dilation effect. So from one perspective, it's the time dilation effect kicking in from our perspective. From the muon's perspective, in a sense, it's a length contraction effect that enables it to get down to the surface of the Earth. In both cases, it matches up with experiment as we have to have it. Otherwise, we'd have a contradiction and something would be wrong. We know the muons get down to the surface, and now we can understand that both from the muon perspective, as it were, and also from our perspective. So, very nice real-life example of the special theory of relativity in action.